Here we are on exercise 7, chapter 2. We are to write code that demonstrates that the dot product is commutative. So what does commutative mean? It's a property in mathematics, and you know what it means, even if you don't remember the term from grade school. But 2 times 3 is the same thing as 3 times 2. So that is the commutative property of multiplication, scalar multiplication. So it's important to demonstrate that any mathematical structures or objects that we want to work with exhibit or don't exhibit commutative property. So the dot product does, you will see later in this book, that matrix multiplication actually does not obey the commutative property. So if these were two matrices, then matrix A times matrix B is not necessarily equal to B times A. They can be equal, but those are actually the exceptions. Okay, so the question is whether the vector dot product is commutative. So this is in terms of scalars, which we know is the case. And if the dot product is commutative, it would mean that A transpose B equals B transpose A. Okay, so first demonstrate this in code and then understand why it is the case. So it turns out that the dot product is commutative using equation 2.9. So I'm actually going to jump to this equation first, and then we'll look at the code. Okay, so here's the formula for the dot product. The dot product is the sum of the element-wise multiplications of vector A and vector B. So because the dot product formula is based on scalar multiplication, and scalar multiplication is commutative, therefore the dot product is commutative. So we could swap the order of A and B, and that wouldn't change the result because, 2 times 3 is the same thing as 3 times 2. Okay, so this is the explanation in terms of the formula. Let's demonstrate this empirically in Python code. Here I define some random vectors of any dimensionality that we want. So I specify 11. I don't know why. Maybe I wrote this code on the 11th day of the month or something. Maybe I was 11 years old when I wrote this code. It was like 6 years ago. Okay, anyway. So 2 random vectors. I'm defining these both to be column vectors, so they're n by 1. And then here I'm manually implementing the dot product. So A times B. And then we sum all of that. I call that ATB for A transpose B. And then here I just flip this around. So this is B times A, and then the sum over all those element-wise multiplications, and I call that variable BTA for B transpose A. Now, if these two are equal, which should be the case if the commutative property holds, then mathematically this is what we want to show, that A transpose B equals B transpose A. And what I am doing in the code here to demonstrate this is just rewriting this equation, so it should be A transpose B minus B transpose A equals 0. So now I'm just leaving out the equals 0 part, and run the code, and let's see what we get. We get 0. Very nice. Run it over and over again. I'm running it lots of times because each time it's going to be different random numbers. Okay, so for an extra challenge, let's see what happens when we use numpy.dot to compute the dot product. Okay, so let's try this. Numpy.dot. Let's do A comma B minus numpy.dot B comma A. And yeah. Okay, so we get an error. And if you are working through this book and you've never had a linear algebra course before, you're brand new to linear algebra, you haven't yet learned about matrix multiplication, this error is going to look really weird and incomprehensible. So what's actually happening, this is a source of much confusion in many students of linear algebra who are using Python. You think that this function implements the dot product because it's called numpy.dot. It does not actually implement the dot product. It implements matrix multiplication, which can be conceptualized as a organized sequence of dot products. So if you actually want to implement the dot product using np.dot, then what you really need to do, so I'm just commenting this out just to show you that this piece of code here is also producing an error. So what you need to do is set up the right orientations for these two vectors. So the first vector should be a row vector, and the second vector should be the column vector. So now that works. Okay, and what is this number? Who knows? This is the dot product of two random vectors, so it's always going to be different. Okay, so then I'm going to transpose this first vector, and now we get a result of 0. So again, the dot product of A and B is the same as the dot product of B and A, which means the dot product is commutative. Again, if this all looks really confusing, I promise it will make perfect sense when you learn about matrix multiplication later in the book.